Okay, so before we had the midterm, I was talking about Kepler's laws, and we'll refresh everyone's memories about what those were in a minute. But I want to take that as a springboard to talk about some overall patterns of seasonality and influence that might have on the climates we find on different parts of Mars, and relate that to the situation we see here on the Earth. So, first of all, you all have experience with climate and weather here on the Earth, right? Yeah, okay. So, first major question is, what's the difference between climate and weather?
Weather is like sort of like right now, like at a specific time.
Is it going to rain today? I forgot my umbrella in the car. Am I going to be... Is that what you're talking about?
Yeah.
Okay.
And climate is like over a longer period of time.
Okay.
Like grander scheme.
Okay. Yeah, so climate would be the regional patterns of temperature and precipitation that we find in areas. So the climate of downstate New York, how would you characterize the climate that we have? What?
I would say cold and rainy.
Well, it's cold and rainy now, but in terms of the climate that we have here, how would you describe it?
Like warmer.
What?
Warmer.
Warmer, okay. How does the climate here compare to the climate in Madagascar or Central America? Costa Rica?
A lot less humid and warm.
A lot less humid and warm where?
Here.
Here?
Yeah.
A lot less warm, okay.
It fluctuates throughout the year with the seasons.
Okay. So what kind of seasonality, I want to focus on that and then we'll get to you, Lizette. What kind of seasonality do we see here in downstate New York? Yeah, but what does that mean? What parameters change seasonally the most markedly here?
Temperature.
Temperature. Okay, so we've got seasonality here primarily in terms of cold winters, hot summers. What about in terms of precipitation? Do we have dry seasons and rainy seasons, dry seasons and wet seasons? No. Okay, so we've got less variation in precipitation, more variation in temperature. We've got, we've got snow in the winter, we've got rain in the summer, but it's not like we've got a dry season. Whereas in Costa Rica, you won't necessarily see the same variation in temperature, but you oftentimes, depending on the location, see very pronounced differences between the rainy season and the dry season. Okay. So the patterns of temperature, the patterns of precipitation, how they vary over the season, that's really what we're talking about in terms of climate. Now, what are kind of the main overall arching patterns that we see? Global patterns of temperature.
Usually near the hemisphere it gets warmer.
Near what hemisphere? Not the hemisphere, near the
Equator.
Near the equator. Okay. So it's generally warmer in the equator?
Cold at the poles.
Cold at the poles? Okay. What about global patterns of precipitation?
It rains a lot, like they have monsoon season, like in India.
Okay. So there's monsoon seasons in India. I don't know that we'll go into that level of detail, but that's due to a particular way that India heating up during certain times of the year draws air currents in off of the ocean, and that those air currents bring moist air, which then leads to a lot of rain. Tropics. What do you think of in terms of precipitation when you think of the tropics? Rainy. Okay. Rainforest, right? Okay. Where do we find big deserts, major areas of deserts? Not so much on the equator.
Like northern Africa and
Northern Africa, Middle East, okay. Sahara, that's a huge band of desert. That's a little bit, that's maybe 20 degrees north of the equator. What other big deserts are you aware of?
Southern North America.
Southwestern North America. Yeah, Arizona, like the Sonoran and Mojave deserts. That's also in that kind of subtropical area.
Antarctica.
What? Antarctica is actually a cold desert. Okay, so both at the North Pole and the South Pole, we don't get a lot of precipitation for a couple of reasons. Okay, we've got those big patterns. I guess then the questions that we'll get to in a little bit of detail, not as much as if this were a physical geography or environmental studies class, but we'll get to some of the controlling factors there. So, more important for our talk today, especially as we want to apply this to Mars, is what causes the seasons. So if we just focus on, the northern temperate area like we experience here in New York, we talked about there being seasonality in terms of temperatures. We get warm temperatures in the summer, cold temperatures in the winter. And it's an interesting study a while back where they asked, dozens of Harvard graduates why it's warmer in the summer and colder in the winter. And one of the most prominent answers they got was, well, in the summer, the northern hemisphere is tilted toward the sun, and that's why it gets warm here during the summer. Does that seem reasonable? Okay, so why do I then have on the bottom of this slide a question saying, why is this a misconception?
It's not because we're physically closer to the sun, it's because we're getting more light throughout the day.
Okay, so the very common misconception is, well, if the northern hemisphere is tipped toward the sun, we're closer to the sun, and therefore have to be warming up more because, the closer we are to the sun, obviously the warmer we are. But the big problem with that is that, the scale is totally wrong here. Anybody know offhand how far away the Earth is from the sun? Miles or kilometers, either one.
92,960,000.
Okay, 93 million miles. So how much of a percentage is the northern hemisphere going to be closer to the sun just by the Earth wobbling back and forth or the tilt of the axis moving around? Insignificant. Okay? So the distance of the northern hemisphere to the sun does not really change with the seasons. It actually does in a way that we'll talk about in a minute, but not the way people think. Okay? So indeed, the reason why we have it's warmer here in the northern hemisphere during the summer is because of the tilt of the Earth's axis, but it's not because that puts us closer to the sun. It's because it puts us more directly in line with the incoming solar radiation. So if I draw a sun over here, again grossly not to scale, and draw the Earth over here, very, very, very not to scale, right? Generally speaking, why is it warmer at the equator than at the poles?
Directly, yes.
Yeah, so the sun is directly overhead. A square meter of incoming solar radiation basically gets blasted onto a square meter of land surface when the sun is directly overhead. But look what's happening up here at the poles. If you have that same square meter of incoming solar radiation, those photons are going to be spread over a much larger area. And so essentially the incoming sunlight is more dilute. It's more spread out across the land surface. The the lower the angle of the sun is in the sky. And so that explains, that right there kind of explains the just overall pattern we saw, that generally speaking it's warmer at the equator, colder at the poles. And then what's the effect of the Earth, the tilt of the Earth's axis changing over the course of the summer, over the seasons?
Causes like different parts of the globe to be in that like direct area.
Right. So during the northern summer time, May through August, June through August, September, the area where the sun is going to be directly overhead is going to be, I can't do this dynamically on this drawing, it's going to be above the equator. It's going to be at essentially 23 degrees north latitude. Okay, the angle of the Earth's tilt determines the maximum elevation of the sun during the different parts of the orbit. And so the situation in New York is that we have the sun is more directly overhead for us during the summer than it is during the winter. And so any incoming solar radiation we get during the summer is going to be more concentrated and going to be heating up the land surface more in the summer than in the winter, when that angle is lower and the incoming solar radiation is spread out over more area. And that basically drives a lot of our weather. I won't take the time to go into this in much detail, but this would be the situation essentially during our either spring or fall equinox, when the sun is directly over the equator. We would basically have a large amount of, or very dense incoming solar radiation here at the equator, less so at the poles. That's going to drive the air around. As the surface of the Earth at the equator heats up, what's going to happen to the air temperatures there? Increase. What happens to warm air?
Rises.
Warm air rises. Okay, so this differential heating causes a convection current that basically has the air at the equator rising up because it's less dense. As that air rises up, it's going to be replaced by air flowing in from higher latitudes. And as this rising air rises, it's going to cool off, and what's going to happen to the moisture that is in that atmosphere? Yeah, as the air cools off, it can't hold as much water. The water condenses out, and that's why you get rainfall, have large amounts of rainfall in this area where these air masses are coming together and rising. Well, for reasons I won't really go into, on the Earth, those convection cells are broken up into 3 convection cells in both the northern and southern hemisphere. You can trace these arrows around. You can see that in the subtropics, in the tropics, we basically have air masses moving toward the equator. And at the subtropical areas, these masses of air that start off at the equator and cool off, they essentially cool off so much they get dense and then they sink down. And here we have the exact opposite of what's going on at the equator. Instead of wet, warm, moist air rising and cooling off and leading to rain, we've got cold, dry air, which doesn't have a lot of water in it, descending. What's going to happen to the temperature of that air as it descends?
It's cold.
No, it's the opposite of what happens when the warm air rises. Warm air rises, it cools off. Cold air falls, it's going to warm up. So you start off with dry air that doesn't have a lot of water in it. And as it sinks, it gets even warmer and can hold more and more water. So it's very unlikely that you're going to get much rainfall there. That's why we have the deserts in the southwest United States. That's why we see this band of deserts across North Africa with the Sahara Desert, the Arabian Peninsula being a large desert, the Gobi Desert in Asia, although that has some other rain shadow kind of effects in it. We see the Atacama Desert down here in South America, some of the driest locations. I mean, there are locations in the Atacama Desert that have had no rainfall recorded for decades because of these descending air masses. No, Ani.
So because of that, like, you know, like how they were saying how it like snows in Egypt, like why would that have been caused?
Well, a particular snowfall would again be, you know, a particular weather example. The climate here are these overall broad patterns. Now, there's nothing that would prevent a cold air mass moving down from, in that case, Europe, meeting up with some warm air masses that are down in the subtropical area, and under the right conditions leading to some snowfall.
But like the heat that's hitting it, you know, that strong heat doesn't affect that anyway.
In terms of overall averages, yes, but I mean the day-to-day weather is, you know, a kind of chaotic pattern that's on top of these overall patterns. Yeah.
So like the Tropic of Cancer, is that pretty much where deserts kind of exist?
Tropic of Cancer and Tropic of Capricorn. So 23 degrees north latitude is pretty much where we find the Mojave Sonoran Desert, the Sahara Desert, the Arabian Desert, pretty much the Gobi, although it's a little, it goes north a little bit because of Asia is just this huge landmass, and you've got the Himalayas that are blocking any flow of moist air. So there are other reasons for having deserts besides just this. But in 23 degrees south latitude, we see the Atacama Desert in Australia, Kalahari Desert in Africa. And any of you been to Australia? You know, what's the interior of Australia like? It's one huge desert, right? Okay, so those are all those bands of dry areas. Okay, so what's Kepler got to do with any of this? Kepler's laws don't have a lot to do with climate on the Earth, but they do influence climate and seasonality in terms of climate on Mars. So I want to talk about how they relate to the Earth first, and then we'll apply it to Mars. Again, Kepler's first law is what? Okay, planets travel not in perfect circles. You know, this was a conceptual breakthrough. Remember that we're not dealing with perfect heavens where everything is in a perfect circle. Planets are traveling around in elliptical orbits, and the planets will vary in terms of how elliptical their orbits are. And we'll see a big difference between Mars and the Earth. So keep that in the back of your mind. We'll forget about the third law because it really doesn't relate to these seasonality things. What's the second law?
Well, it moves faster than perihelion?
Yes. So perihelion is what?
Closest to the sun.
Okay. So if the planets are moving around the sun in elliptical orbits, then part of the orbit's closer to the sun, part of the orbit's farther away. And when the planet is closer to the sun, it's moving faster, it's really bugging out, and when it's at aphelion, it's at its slowest point in the orbit.
Is this equal area? Could that mean like equal amount of radiation because it's moving faster? So like, regardless on what side it's on, the weather kind of stays the same.
Yeah, that's a little bit of a push. I mean, this this formulation of sweeping out equal areas and equal times is, it's the underlying geometry of the situation is how Kepler phrased it, but I always find it very weird to think of it in terms of that, or this windshield wiper effect as the one video talked about. The main point is that the orbital velocity is directly related to where in the ellipse the planet is, and planets speed up and slow down. Colin?
Is it really like that scale?
No.
No, okay.
No planet in our solar system is as elliptical as this.
Yeah, I was gonna say, like that's.
That would be like, it'd be very difficult to, maintain a habitable environment in a situation like this. Okay. In fact, if you look at the orbit of the Earth, just using your eyeball, you would swear it was a circle. Okay. And even Mars's, as we'll see in a minute, you can tell that Mars's orbit is elliptical compared to the Earth's, but it's still pretty circular. Okay, so remember the first and second laws, especially the second laws we talk about. Okay, so here is essentially, as I talked about, the orbit of the Earth. Looks fairly circular, but it's not. Oh, I thought I had added. The eccentricity for the Earth which is the measure of how non-circular or how elliptical the orbit is. I added this to the Google Doc. I guess I didn't add it to the presentation here. Is about 0.01 something. Colin, quickly look it up. Earth orbit eccentricity. So, it's essentially circular, which means what about the change in velocity of the Earth's orbit as it goes around the sun? Yeah, Colin?
It's 0.0167.
67, okay. It's not a perfect circle, so there are going to be times when the Earth is moving faster and times when the Earth is going to be moving slower. And when is it going to be moving faster?
July.
Why do you say July?
It's the Philion, and it's the closest.
No.
Oh, right. No, I have it switched.
Yeah. The A here, the little A here is aphelion. So that's when the Earth is farthest away. The little P is perihelion.
Perihelion.
So in January, during our winter, the Earth is moving along a little bit faster in its orbit than it is in July during our summer. Okay. But as I said, in the case of the Earth, it's really not that much, because if you look at, so we would have, in addition to the aphelion and perihelion, which determine how close and far away the Earth is from the sun, we also have the solstices and the equinoxes, right? So what is the summer solstice? June 21st, about right here. And so December 21st, 22nd is the winter solstice. What's defining that? Has to do with the tilt of the Earth. Elise. No?
When it's tilting the most.
Right. So June 21st, 22nd, whenever it is, the northern hemisphere, the North Pole, is tilting most directly toward the sun.
Why would it be directly on the perihelion and aphelion?
The ellipticalness of the orbit, the eccentricity of the orbit, is not constrained or related to the particular tilt of the planet. So I mean, it's hard to even, draw this, but essentially, if we talk about the Earth at this point, it's like a spinning top, but the axis of that spin is going to be in this direction. As the sun moves around, as the Earth moves around in its orbit, that axis remains. And so by the time you get around to the winter solstice, now we've got the tilt of the Earth from a northern hemisphere perspective pointing away from the sun. And of course, what's happening in the southern hemisphere? Pointing toward the sun. Okay. And so then what is happening on March 21st or whatever when we're at the spring or vernal equinox? Midway through, the spin axis of the Earth, the tilt of that spin axis is essentially perpendicular to the line drawing toward the sun. And that's why at that time of year we basically are talking about having the equal day and night time. Okay. The same thing here with the fall equinox in September. Again, the tilt of the spin axis of the Earth is perpendicular to, the direction toward the sun. So you kind of wrap your head around that. But if you think of the Earth as just this spinning top, and the spinning of the top kind of provides a buffer, keeping it pointed in the same way. What if you spin a top real fast? It's fairly stable, right? And then what happens as the speed of the spin declines? Wobbles, and then eventually it doesn't maintain. Okay, Earth has a lot of angular momentum involved in that spinning axis, and so as it's going around the sun, the direction in space that the Earth is pointing to really doesn't change. Now we could stretch and squish this orbit however we want. Make this the aphelion and this perihelion. The spin axis isn't going to change. So there's no necessary correlation between the spin axis of a planet and what point in its orbit it is closest or farthest away from the sun. In the Earth's case, like I said, we've got aphelion here in July and perihelion in January. Doesn't really match up with the solstices. So we've got the one solstice there, the one solstice there. It doesn't match up with the equinoxes either. So, in describing this orbit, we can draw these lines that kind of represent where the arrangement of the solstices and equinoxes are, and that's really driven by the spin axis of the planet. And then we can indicate where the aphelion and perihelion are, and that's really driven by the eccentricity of the orbit. And there's a whole ton of other orbital parameters we could be talking about. The tilt of the axis in relationship to the spin axis of the sun, how this all relates to the galactic plane and all that stuff. But this is more than complicated enough, right? Now it's interesting, in the case of the Earth, and I've got a link down here, you can follow this later. The Earth as a whole is actually warmest when it's here at aphelion, the furthest away in its orbit from the sun. And that's really a quirk of our planet. How do the continents and oceans compare in the northern hemisphere versus the southern hemisphere on the Earth? A lot more land in the northern hemisphere. A lot more ocean in the southern hemisphere. We've got Europe and Asia, North America. We've got Africa and South America and Australia, but Australia is kind of an island continent. And in terms of Africa, a large portion of it's actually north of the equator. So if you look at the southern hemisphere, it's a lot of open ocean. You look at the northern hemisphere, and it's a lot of landmass. And that landmass actually heats up rapidly in the summer and cools off rapidly in the winter. So when the Earth is actually farthest away from the sun, it just happens to be that that's also during the northern hemisphere summer, and you've got all that landmass soaking up the solar radiation. So if you actually look at the global mean temperature, paradoxically, for the Earth, it's actually the highest when the Earth is furthest away from the sun.
Is it because the sun covers so much more area at once that it's globally seen as warmer?
No,
Because it's warmer in more places than it would be when it's closer to the sun, where it's warmer.
it's a matter of, I mean, we're measuring air temperatures here, right? So when the Earth is over here and the southern hemisphere is pointed more toward the sun, you've got all that solar radiation hitting the oceans. The oceans kind of suck that up without warming up so much. Because it's not warming up, it's not heating up the air, and therefore it's not contributing to the global mean temperature as much.
I know there's like an east-west hemisphere you can draw where like almost half the Earth is completely water. I think it's called the aquasphere or something. There's at a certain point where you can cut it down and like half of the Earth can be mostly water.
Yeah, I mean, you'd want to have Africa, Europe, Asia, and Australia, on the one side. Then you just have North and South America on the other side. You'd have a lot more water, but because of the way the Earth is spinning in space at that kind of difference really doesn't matter as much as the concentration of land masses in the northern hemisphere versus the southern hemisphere.
But the tilt somehow manages to stay like throughout every rotation. It's in the same position at every position pretty much. So there's some sort of relation between the orbit and the tilt, I'm guessing, because they seem to be in the same position every year.
Right. That's because of the spin, as I talked about, has this angular momentum that kind of stabilizes the Earth. Now, the Earth is, though, still a spinning top, and even before a top gets completely unstable, it can wobble a little bit, right? That wobbling is called precession. The Earth does precess. But currently, our North Pole is pointing at Polaris, which is a star in the Little Dip, right? And that's why Polaris is called the pole star, because it's pretty much directly above the North Pole currently. If we're all around in 25,000 years, Polaris is not going to be the North Star anymore, because the Earth will have slowly precessed around. And I don't have off the top of my head what that precession cycle is. It's on the order of tens of thousands of years. The eccentricity of the Earth also wobbles back and forth over a longer time period. And the relationship of the spin axis of the Earth to that changing eccentricity itself changes over time. And so you get these very long period cycles that have influences on climate. Part of what's driving, when we have ice ages and when we don't. So, I'm just going to mention that stuff. I'm not going to really get into it all. The main point is that we've got aphelion, perihelion, we've got the equinoxes and the solstices, we've got the spin axis of the planet, and on the case of the Earth, all that doesn't have much impact on our seasonality. Generally speaking, it gets warm during the summer up here because of the tilt. It gets cold during the winter because of the tilt, and we get the opposite kind of seasonality in Buenos Aires, Argentina, or Sydney, Australia.
Thank you.
Okay, so here's the situation with Mars. If you look at the orbit of Mars, can you kind of tell even by eye that it's not quite as circular as that for the Earth?
Yes.
Okay. So it's not nearly as bad as those diagrams that are always used to illustrate Kepler's laws. Like I say, no planet in our solar system is anywhere near that eccentric. The eccentricity for Mars is something like 0.09 something, 23 maybe. Which is about 6 times as eccentric as the orbit for the Earth.
It's 0.0935.
35. Okay. So, again, we can define where Mars is at perihelion, which is over here, and at aphelion over here. Again, we can define the equinoxes and solstices. The equivalent of the spring equinox for Mars occurs off in this direction in its orbit. So, you know, if we happened to be here on the Earth and during our winter, and Mars happened to be in its part of its orbit as it was here, you know, during our winter, Mars would be going just essentially starting spring in the northern hemisphere. Same thing here, fall equinox, consistent. Northern hemisphere summer solstice occurs at this orientation, and the northern hemisphere winter solstice occurs over here. Okay, so where in Mars's orbit is it going to be traveling the slowest? We've got all these circles here. Colin.
By this, where it says solstice,
Here?
but next to 90 degrees next to July.
Not quite.
Around the 6-degree mark.
Here?
Yeah.
No.
No.
Where is aphelion?
Oh, I just said it.
Right here. Okay, so here is
We were so close.
here is the slowest part of Mars' orbit. So conversely, where is Mars going to be traveling the fastest? Okay. So I'll draw a long arrow here indicating that Mars is traveling relatively fast. Short arrow here indicating that Mars is going slow. And farther from the sun here at aphelion, closer to the sun here at perihelion. Okay. So again, these don't necessarily have to line up with any of the solstices or equinoxes. They're kind of close to the solstices, which happens to be a situation with the Earth, but that's just fortuitous. Okay. So if we think of spring equinox to summer solstice in the northern hemisphere as the northern hemisphere spring, so I'll just say northern spring here, and northern summer here, well, which is what's indicated here, and northern fall, and northern winter. Which of these seasons are going to be longer and which seasons are going to be shorter? Somebody else. This is an easy question.
Summer, spring.
Summer, spring in the northern hemisphere, they're going to be longer because because Mars is traveling more slowly. And northern fall and northern winter will be shorter.
If thought it was equal areas.
Well,
Because it's still traveling slower, but it's like a short.
the velocity and the distance to the sun in that area is equal, but the solstices and the equinoxes are always defined in terms of the spin axis, which is going to be defining these 90-degree quadrants. Okay? So this is not a Kepler second law pie chart here. This is what part of the Mars calendar year do we call northern spring, and because Mars is traveling away from the sun, it's slowing down, and that's going to lengthen out the length of the northern spring. And Mars is starting to speed up as it's going back closer to the sun here, but this is still, overall the slower part of its orbit. So whereas the days of the seasons on the Earth don't vary all that much, given the greater eccentricity of Mars' orbit, you would expect that it would be more variable, and indeed it is. We essentially have the northern spring lasting 194 sols, and northern summer lasting 178 sols, and northern fall 142 sols, and northern winter 154 sols. Again, what is a sol? A day on Mars. Okay. So right off the bat, we have a lot more variation in the length of seasons on Mars than we do on the Earth.
That means sun in Spanish.
What?
That means sun in Spanish.
It does. Yes. Probably also Latin, I think.
Yeah, it means that.
Yeah. So, on top of that, we have a much greater variation in orbital distance from the Sun for Mars than we do for the Earth. So, where is Mars going to be receiving a higher influx of solar radiation? At aphelion or perihelion? Perihelion. Okay, so more sun here and less sun here. Okay, longer season here. Northern summer, southern winter. So northern summer takes place at the part of the orbit where Mars is farthest away from the sun. Well, northern spring actually. And southern fall / going into winter also happens when Mars is farthest away from the sun. Okay, so if we put this all together, seasonal variation in the southern hemisphere of Mars is much more extreme than seasonal variation in the northern hemisphere. Why is that? This will be a good final exam question.
Is it because of the revolution of the sun?
What exactly do you mean by revolution of the sun?
How it goes slower in certain areas.
Okay.
So it should be Kepler's second law?
Kepler's second law would be involved here, and the first law. If the planet is further away from the sun here, that's during the summer in the northern hemisphere, but winter in the southern hemisphere. What impact will having less solar radiation during the southern winter have on the severity of the winter? So you're going to basically have, in the northern hemisphere, you're going to have a cool summer because it's summertime. The tilt of the planet is toward the sun, but Mars is further away from the sun, so significantly further away from the sun. So it is summer, but it's not a real warm summer.
So then the winter will be much more mild?
Over here, the northern winter?
No. No. Yes. No?
Yeah. So, yeah.
Yeah.
Northern winter would be kind of a mild winter. This is during the winter time for the northern hemisphere, but it's also when Mars is closer to the sun. So the weather's getting crappy, but the fact that Mars is close to the sun helps out a bit. So the northern hemisphere basically is going to have, in Mars terms, coolish summers and mild winters, whereas the southern hemisphere, when it's winter, Mars is also far away from the sun, it's going to be a really, really cold winter. You know, to the tune of minus 100 and some degrees cold. And over at this part of the orbit, when we have the southern summer, not only is the southern hemisphere experiencing summer, but it's also relatively closer to Mars. So this is about as hot as it's going to get on Mars, essentially during the southern summer. But the southern summer is also the short season because Mars is speeding through its orbit at that point. So the southern hemisphere has short, hot summers and long, cold winters. And the northern hemisphere has short, mild winters, relatively speaking, and long, cool summers. You know, it's warmer, but it's, you know, not yeah. So, where do you want to go live on Mars? Northern hemisphere. Okay, that's the take-home message. No candidates for a one-way mission to Mars?
Yeah, that was a scam.
I'll do it.
Yeah, that's what I heard.
Yeah, Mars One may or may not be a scam. I mean, there may be some people who think that they can pull this off. I will believe it when I see some hardware actually being produced. But it is quite likely. I mean, I don't know if we'll have time to talk about this when we talk about the future part of the course, but it is quite likely that a viable strategy for the initial missions to Mars are indeed one-way missions. It's a lot easier to get to Mars. Having to return makes it a lot more difficult. And so, you know, if you've got people who are willing and the system is ready to support colonization, it would make some sense for our initial missions to Mars to be colonization missions. Because then you don't have to worry about, you know, actually having the infrastructure on Mars to be able to send the people you sent to Mars back to the Earth. So is Mars One a scam?
Yes.
Probably.
The finalists like never actually have met with anyone from the
Yeah.
which is kind of